Welcome to the deep dive. When you dive into physical chemistry, even something seemingly simple like, well, air, suddenly gets this incredibly rigorous treatment.
It really does.
So today, we're getting into that foundational stuff, the properties of gases. We're basically distilling the key ideas from the molecular thermodynamics and kinetic sources.
Exactly. And our goal here really is to give you that core structure, because physical chemistry, it doesn't just describe gases, it builds this whole way of thinking.
And that methodology. Yeah.
Right. We'll go through it in three main steps. First, the perfect gas, that's our idealized starting point based on observation.
Okay.
Then, the kinetic model. That's the why, the molecular picture behind that ideal behavioral.
The engine room, basically.
And finally, we tackle real gases.
Yeah.
Because let's face it, the real world isn't quite perfect. We need to account for those pesky molecular interactions.
Perfect. Kinetic, real. Got it. So let's start with that foundation then. The perfect gas. You mentioned it all comes down to just four variables defining the state.
That's right. The state of any substance, fundamentally, is pinned down by just four things you can measure. The amount of substance, which we call final.
Okay, moles.
Moles. Then volume, vialer. Pressure, paddle. And temperature, $2.
And the idea is, if you know three, the fourth is fixed.
Exactly. That's what an equation of state does. It connects them. You specify three, nature tells you the fourth. No wiggle room.
Okay, let's unpack pressure. The source had this great description. Pressure is the result of the incessant battering of molecules against the container walls.
I love that phrasing. It really captures the microscopic reality. It's not a smooth, static force. It's countless tiny collisions adding up.
Billions per second.
Right. And when we talk about mechanical equilibrium, say, between two gas chambers with a movable wall, it just means the battering rate is equal on both sides. The forces balance out.
Makes sense. And units, Pascal is the SI unit, but we often see bar or atmospheres.
We do. Bar and Atkill are just more convenient scales for everyday pressures, like weather or typical lab conditions. But fundamentally, it traces back to pascals, which is force per unit area.
Got it. Now, temperature, $2. You emphasized this earlier. We must use the thermodynamic scale, right? Kelvins.
Absolutely critical. Always kelvins, capital $20. That conversion from Celsius, theta, is precise. $2 in Kelvin equals degrees Celsius plus 273.15.
Hey, don't forget the 0.15. It matters for precision. This thermodynamic temperature is what actually drives the behavior described in the gas laws.
Okay, so we have 1 ReB PT2. How do they relate in this perfect gas world? That leads us to the big one, PV ORT OT.
The perfect gas law. And it's beautiful because it wasn't just pulled out of thin air. It's actually a combination of three simpler laws discovered empirically just by watching how gases behave.
Right. These were observed patterns first. Let's quickly touch on those. First up, Boyle's law. Boyle noticed that if you keep the amount of gas, no dollars in the temperature, constant, then pressure and volume are inversely related. PV equals some constant value.
So if you squeeze it, the pressure goes up proportionally.
Exactly. And if you plot pressure versus volume at constant temperature, you get these characteristic curves, hyperbolas, called isotherms.
Okay, then Charles's law brought in temperature.
Yes. Charles found two things, really. At constant pressure, volume is directly proportional to temperature. E dollar prop O2. Heat it up, it expands. Those plots are lines called isobars.
And if you hold the volume constant...
So then pressure is proportional to temperature. P prop OT. Heat a sealed container, the pressure rises. Those lines are isochores.
And the key insight there was extrapolation to absolute zero, right?
Well, that was huge. All those lines, when traced back, pointed to this theoretical temperature where volume or pressure would hit zero, absolute zero Kelvin.
Okay, Boyle is PVS, Beedrow, Charles is $2. What's the third piece?
Avogadro's principle. This connects volume to the amount of gas. At constant pressure and temperature, the volume is directly proportional to the number of moles, propto siderenardo. More gas, more space.
Simple enough.
But here's the crucial bit, the fine print everyone forgets. All these laws, and therefore the combined perfect gas law, PV-NRT-JA, they're limiting laws.
Meaning?
Meaning they are only perfectly accurate in the limit as the pressure approaches zero.
Ah, because at zero pressure, the molecules are infinitely far apart.
Exactly. They don't interact. They don't notice each other's size. That's the definition of perfect behavior in this context.
So PV-NRT is this idealized baseline.
Yeah.
And $3 is the molar gas constant.
Right, the universal constant that makes it work for any gas behaving ideally. That universality is really profound.
Okay, so that works beautifully for one pure gas. But what about mixtures like the air we're breathing right now? Nitrogen, oxygen, argon.
Good question. We need a way to talk about the contribution of each component. That's where mole fraction comes in.
Mole fraction, $6 off.
Yep.
For any component, let's call it G in Euler, its mole fraction 6 hectorjoules is just the number of moles of n joulers divided by the total number of moles. It's literally its fraction of the total amount.
Simple ratio. And how does that relate to pressure?
That leads directly to partial pressure, PJ-Eulers. The definition we always use is that the partial pressure of component joulers is its mole fraction times the total pressure. PJ is XJPJ.
Okay, PJ if we use XJP. That definition always holds.
Always. This definition is the modern, rigorous one. Now, Dalton's law states that the total pressure is simply the sum of all these partial pressures.
So PG equals PA plus PB plus PCO and so on.
Exactly. Now, the original way Dalton thought about it was the pressure a gas would exert if it were alone in the container. That version only strictly works for perfect gases. But our definition, PJ equals XJPTD and the sum rule. That works for any gas mixture.
That's a useful clarification. So let's apply it. Dry air is roughly, 78% nitrogen, 21% oxygen, 1% argon by mole.
Approximately, yes. Those are the mole fractions, essentially. $6, 0.781, total is 0.21 of pro, 0.211 of relative, delivered to 0.011. So if we're at sea level, roughly 1 bar total pressure. What's the partial pressure of oxygen, PO2, Dalton?
You just apply a definition, PO2 times P2O2 times P total. So that's $0.21 times 1 text bar.
Which is 0.21 bar.
Simple as that. And knowing those partial pressures is fundamental for everything from understanding how we breathe to designing chemical reactors.
Okay, that grounds the perfect gas law nicely. Yeah, let's shift gears. We know the what, PV and RT2. Let's get to the why. The kinetic model of gases, or KMT.
Right, the molecular machinery behind the laws. And remarkably, it starts with just 3 very lean assumptions, almost radically simple.
Okay, assumption 1. Molecules are in ceaseless random motion obeying classical mechanics. That seems intuitive enough.
Yep, they're just bouncing around according to Newton's laws.
Assumption 2. Molecules have negligible size. They're treated as point masses. Now, hold on. How can we just ignore their volume?
That's the key simplification that makes it a model for the perfect gas. If they have no volume, they can't bump into each other in the sense of taking up space. It avoids short-range repulsion. It's directly tied to that right arrow dollar limit where real gases behave ideally.
Okay, so it's a deliberate idealization.
Yeah.
Point masses, what's assumption 3?
They interact only through brief, elastic collisions.
Elastic meaning kinetic energy is conserved.
Exactly. When they hit a wall, or very occasionally each other in this model, they bounce off perfectly. No energy lost to heat, no sticking together, no attractive forces at all.
So point masses, constant random motion, only perfectly bouncy collisions. That's it.
That's the core of the model. And
Yeah.
from just those 3 ideas, we can mathematically derive the pressure.
How does that work conceptually?
Well, you think about one molecule hitting a wall, it bounces back, so its momentum changes. Force is rate of change of momentum.
Okay.
So you calculate the momentum change for one collision. It depends on the molecule's mass and its velocity component towards the wall, 2 milliviers. Then you figure out how often molecules hit that wall, considering their speed and the number of molecules per unit volume.
And you average over all the molecules?
You average the effect, yes. And when you crunch through the math, accounting for motion in all 3 dimensions, you arrive at this fundamental result. P up V 349 V2 angle.
Okay, P equals 1/3 times amount times molar mass divided by volume times, what's the angle V2?
That's the mean square speed. It's the average of the squares of the speeds of all the molecules.
And the amazing thing is, this equation derived from molecular mechanics perfectly matches Boyle's law, right? If temperature dollars is constant.
Then the average kinetic energy is constant. And since kinetic energy is related to μ V2, the mean square speed Langle V2 wrangle depends only on temperature. So if T-Dil is fixed, Langle V2 wrangle is fixed. Look at the equation. PV, it's sprakel we find for Zeden Forel, go on 3, V2 wrangle. Everything on the right is constant.
So PVD equals a constant. The KMT predicts Boyle's law from first principles. That's powerful.
It really is a cornerstone achievement. But there's a subtlety. Molecules don't all move at the same speed. Collisions constantly redistribute energy.
Right, some are fast, some are slow. There must be a distribution.
Precisely. And that distribution is described by the Maxwell-Boltzmann distribution of speeds, usually written as 5D. It tells you the fraction of molecules that have a speed between $5 and $5 plus dVu.
If you picture that distribution curve, it starts at 0, goes up to a peak, and then tails off. Right?
Exactly. It's not symmetrical. Let's think about way. There's a factor of TVO2 in the function, which means the probability of having zero speed is itself zero. You need some speed to even be moving.
Okay, so it starts at 0. Why does it fall off at high speeds?
That's down to the exponential term, EMD22RT2. That theta2 in the exponent means the function decays very rapidly as speed $1 gets large. Very high speeds correspond to very high kinetic energy, and it's just statistically unlikely for a molecule to gather that much energy through random collisions.
And the nollerns in that exponent.
They control the shape. A large molar mass, $, makes the exponent more negative, so the decay is faster. Heavy molecules are, on average, slower.
Makes sense.
And a high temperature, $, makes the exponent less negative, slowing the decay. So higher temperature pushes the whole distribution towards higher speeds. More molecules are moving faster.
So this distribution gives us a detailed picture, and from it we get different ways to talk about the average speed.
Yes, there are 3 main speed metrics derived from the distribution.
Okay.
First, the most probable speed. That's the speed right at the peak of the distribution curve. The single most likely speed, it's squared OT.
Then the mean speed.
That's the straightforward average speed calculated from the distribution. It's slightly faster than $. It comes out as squared $.
And the last one, the one in the pressure equation, was the root mean square speed.
The root mean square speed. You square all the speeds, find the average of those squares, Boltzmann, and then take the square root. This one gives more weight to faster molecules and is the highest of the 3. So Weyman varms, but they're all related to the score TMs.
Correct. They all increase with temperature and decrease with molar mass.
Now, if these molecules are zipping around, they must be colliding. How often does that happen? That's the collision frequency.
Right. So Amber's is the average number of collisions one molecule makes per second. It depends on how fast they're moving and how crowded it is.
So higher temperature means faster speeds, means more collisions. Zibble goes up with $2.
Yes. And higher pressure means higher number density, more molecules packed into the same volume, so they bump into each other more often.
Yeah.
Symbol is proportional to pressure.
Okay. And the flip side of frequency is distance, the mean free path, lambda.
Exactly. Lambda is the average distance a molecule travels between collisions. It's basically the average speed divided by the collision frequency, lambda varens. The example given for nitrogen at room temperature and pressure was about 91 nanometers. That sounds incredibly short.
It does, but think about the scale. A nitrogen molecule itself is maybe, what, 0.3 or 0.4 nanometers across?
Ah, okay. So 91 millimeters is actually hundreds of times its own diameter.
More like 1,000 times its diameter, roughly.
Yeah.
So yes, they move fast and collide often, but they actually spend most of their time traveling freely between those collisions. It's not like bumper cars in constant contact.
That's a really helpful visual. Okay, so we've built up the perfect gas from empirical laws and then explained it with the kinetic model. Now, the reality check. Real gases. Why do they deviate from PV-nRT dou?
Simply put, because the KMT assumptions break down under certain conditions. Real molecules do have size, and they do interact with each other.
And these deviations become significant
when the molecules are forced close together, which means high pressure, or when they are moving slowly enough for interactions to matter, which means low temperature.
Let's break down those interactions. There are 2 main types, right? Repulsive and attractive forces.
Correct. Repulsive forces are very short range. They dominate only when molecules are practically touching. Think of them like tiny billiard balls resisting being squashed into the same space.
So at very high pressures, these repulsions make the gas harder to compress than ideal.
Exactly. The volume is larger than the perfect gas law predicts because the molecules themselves take up space. The gas is less compressible.
Then there are the attractive forces. These are longer range. Van der Waals forces, dipole, etc.
Right. These tend to dominate at moderate pressures and lower temperatures. They pull molecules slightly towards each other.
So attractions make the gas easier to compress.
Yes. The attractions effectively reduce the pressure exerted on the walls compared to the ideal case. Or you could say they help pull the gas into a smaller volume. The gas becomes more compressible than a perfect gas.
So we have this tug of war between repulsion at high pressure and attraction at intermediate pressure. How do we quantify how imperfect a real gas is?
We use the compression factor, capital $. It's like a scorecard for gas behavior.
How's it defined?
Zit is the ratio of the actual molar volume, VME calls VMN, to the molar volume predicted by the perfect gas law. So Zit is frac BVMR.
Okay, Z and PVM RT down. So Z and RT.
Perfect gas behavior. An A+ on the scorecard.
If Z and molecules.
Repulsive forces are dominating. The molar volume is larger than ideal. less compressible.
And if Z annullers?
Attractive forces are winning. Molar volume is smaller than ideal, more compressible.
And plotting zeta versus pressure usually shows a dip below 1 at low pressures,
Yeah.
attraction, and then it rises above 1 at high pressures, repulsion.
That's the typical shape, yes. Although the depth and position of the dip depends strongly on temperature.
Is there a special temperature where the initial dip disappears?
Yes, that's the Boyle temperature. It's the temperature at which, as pressure approaches zero, the zitter curve starts out perfectly flat, 0, 1, 1 with zero slope. At T-Bolar, the attractive and repulsive effects cancel each other out over a decent range of low pressures, making the gas behave almost perfectly.
Interesting. Now, this interplay of forces is also deeply linked to condensation, right? Liquefying a gas.
Absolutely. If you take a real gas below a certain temperature and compress it isothermally, keep T constant, you'll see something dramatic happen. The pressure increases as volume decreases, but then...
It hits a flat plateau on the PV diagram.
Exactly. Along that plateau, as you continue to decrease the volume, the pressure doesn't change. What's happening is condensation. Gas is turning into liquid at a constant pressure, which is the vapor pressure at that temperature.
Until all the gas is liquid, then the pressure skyrockets because liquids are hard to compress.
Right, but if you do the same experiment at a higher temperature, that plateau gets shorter.
And eventually it disappears entirely.
Yes. There's a specific temperature for each substance called the critical temperature. Above Tc, no matter how much pressure you apply, you cannot liquefy the gas into a distinct liquid phase.
So above Tc, it just gets denser and denser.
Into what we call a supercritical fluid. It has properties of both liquids and gases. The point defined by T sub T, the pressure needed to liquefy at Tc, and the corresponding molar volume are the critical constants of the substance.
Okay, so the perfect gas law is obviously inadequate here. We need an equation of state that can handle these real gas effects, including the critical point. Enter van der Waals.
Johannes van der Waals. His equation was a brilliant modification of the perfect gas law, introducing just two parameters, a May and other dollars, to account for the interactions. It's a prime example of physical modeling.
Let's look at the equation. P frec n 2. Two corrections there. First, the volume term. The Wallers is replaced by 5NB. What's Dunbuller?
The $NIMBY term represents the excluded volume. It's the correction for the finite size of molecules. Van der Waals argued that the free volume available for molecules to move in isn't the whole container volume Bollers, but $5 minus some volume effectively occupied by the molecules themselves. The Bollers is roughly related to the actual molecular size.
So it accounts for the repulsions. It makes the effective volume smaller, which would increase pressure compared to ideal.
Exactly. It addresses the molecules have size issue.
And the second term, NMBD, this subtracts from the pressure.
Yes, this term accounts for the attractive forces. The idea is that molecules in the bulk of the gas pull back on molecules nearing the wall.
Reducing their impact speed or frequency?
Both, effectively. This reduces the pressure exerted on the wall compared to what it would be without attractions. The strength of this effect depends on how many molecules are near the wall, proportional to density, and how many are pulling them back, also proportional to density, hence the NV2 dependence. The parameter reflects the strength of these attractions.
So Boller handles repulsion size, Dollar handles attraction. It's elegant.
It is, and it's remarkably successful. It predicts the isotherms qualitatively well, it predicts condensation, and it even predicts the existence of a critical point.
Does it get the critical constants right?
It allows you to relate the critical constants, TTP, VC, directly to the parameters 8 and $. Interestingly, the van der Waals equation predicts that for all gases, the critical compression factor, ZCVT, BC VMSC V RC1 should be exactly $388 or 0.375.
And how does that compare to reality?
Real gases typically have ZC values closer to 0.3, so it's in the right ballpark, but not perfect. It shows the model captures the essence, but is still an approximation.
Still impressive for just two parameters. Now, with different gases having different Avenel values, their behavior varies. Is there a way to unify this?
Yes. The final concept here is the principle of corresponding states. It's a way to see the universal patterns hidden beneath the specific values of $.
How does it work?
You define reduced variables. You take the actual pressure, volume, VMV, and temperature dollars and divide each by its corresponding critical constant. Pi PES, PPCO, $4, VMVME, Tautor, tautors, TT,
Okay, dimensionless scaled variables.
Exactly. The principle of corresponding states then says that, to a good approximation, all gases obey the same equation of state when expressed in terms of these reduced variables.
Meaning if you plot reduced pressure versus reduced volume for different gases at the same reduced temperature, the curves should overlap.
That's the idea. Real gases in corresponding states, same dollars and $1, exert approximately the same dollars. It tells us that the deviations from ideal behavior, driven by, I don't know, dollars, follow a common pattern across diverse substances when scaled appropriately. It's a powerful tool for predicting properties when you only know the critical constants.
Wow, okay. That's quite a journey. We went from the simple empirical PV nRT limit.
Then built the molecular explanation with the kinetic model, deriving pressure from molecular motion and speeds.
And finally, corrected for reality, using the compression factor, the ZR, and the van der Waals equation, understanding phase changes and unifying behavior with corresponding states.
It really showcases the core method of physical chemistry, doesn't it? Start simple, explain mechanistically, then refine the model to match the complexities of the real world. That back and forth between idealized models and experimental reality is key.
Absolutely, and hopefully understanding this framework helps you tackle the specific examples and problems in the text. Thanks for taking this deep dive with us.
Yeah, keep thinking about those molecules battering the walls.